Okay, hello everyone. Could you hear me? Hello. Could you hear me?
You're audible, ma'am.
Yes. My screen is visible.
Yes, is it?
Okay. Yeah, thank you very much. Hello. Yes, yes. Hi, how are you? Sorry, could you repeat it again? I can't hear well your voice.
Actually, ma'am, what she's saying, you can start the session, ma'am.
Oh, okay, okay. Thank you. Thank you very much. Okay. Hello, good morning, everyone. Good afternoon, someone who is outside of India. My name is Faranak Solat, and right now I'm working as an assistant professor in the School of Artificial Intelligence and Data Science at Sejong University in South Korea. Nice to meet you all, and this is a great pleasure to me to be here. And first of all, I would like thank you to the organizers for inviting me for the speaking for today lecture in this conference. Today, I'm gonna talk about federated learning meets large language models focusing more on challenges, opportunities, and future directions. Okay, so first of all, okay, let's see. Um, Definitely you know about the large language models, and maybe since decades ago, you already trained a number of machine learning models in centralized learning scenario, right? So you can consider, for example, about like 20, 30 years ago, when researchers try to maybe work with many different datas in centralized learning, most of the time, many clients already has the connection to one centralized server for training, right? And at that time, the amount of data wasn't like these days huge. So transmitting these types of raw data to the centralized server was easier than these days, right? Although at that time there was like the bandwidth limitation and something else, but in comparison with these days, the amount of data and transmitting those ones was kind of easier than these days. But since like 2010 and after that, people try to care more about the privacy of data, and many attacks and many eavesdropping and other types of attacks already developed and exist around the world. So to prevent those things, especially these days, focusing more on the large language models, short form LLMs, there's some room to discuss, especially for research, writing papers, and also collaborating with industries. So, first of all, let's begin with the central question of this presentation. Can large language models learn from our data without collecting our data in one centralized location? And today, much of the most useful information is distributed across different organizations and devices. Like hospitals can already gather many records, like clinical records, and enterprises also have internal documents, like many companies. And also in other side, we have different types of smartphones, and these ones contain highly personalized user data. And also the edge devices, these days we use a lot of those ones, continuously generating contextual and real-time already information. So these data sources can significantly improve the performance and usefulness of the large language models, definitely. But transmitting, as I mentioned, this huge amount of data these days, like big data, many personal data, as to the centralized server will be a number of problems related to the privacy, data ownership, like security and regulatory, like compliance. So one of the maybe answer to these kinds of concern is focusing more on some distributed learning such as federated learning. The federated learning, maybe most of you heard or worked on this area, already offers a different like paradigm. Instead of moving the raw data to the centralized server, each client can keep that one in each location, in keep their own data set, the local one. I will explain a little bit with more details in other slides, and later training the model locally and send the maybe gradients or adapters and different types we already have that I'm gonna explain to the centralized server for model aggregation and updating the global model. Okay, so let's see. If I wanna focus more on federated learning and other types of distributed learning, instead of sending the raw data to the centralized server. So the data paradox will be exist, and we have to consider this one, that keeping the balance between the large language model needs and the data ownership. So in case of LLM, LLMs face what we call a data paradox. On one side, the left side, these models require diverse, high quality, and continuously updated data. Like a general purpose model may perform well on common tasks, but domain specific applications require specialized knowledge. For example, a medical language model needs information from different hospitals, right? Like specialists, patient populations, and clinical procedures. And the other example, an enterprise assistant needs access to internal policies, technical documents, and organizational maybe knowledge. A personalized assistant needs to understand the performance and behavior of individual users, right? And the other side, on the right side in this figure, we already have the data owners must protect the privacy, confidentiality, intellectual property like IP, and regulatory compliance. So in many cases, organizations are legally or commercially unable to transfer their own the raw data to an external centralized platform, right? So what should we do? Therefore, the objective is not simply to collect more data. The real objective is to make distributed knowledge useful while reducing the movement and exposure of raw information. This tension creates a strong motivation for federated learning. Okay, so after considering this thing, I'm gonna talk about the roadmap. It's including 6 different parts. The first part, I'm gonna start with why LLMs need distributed learning, and then focusing on federated learning foundations, simply explaining what is it, and then federated adaptation of LLMs, then core technical challenges, and then applications and emerging opportunities. And the last one, future research directions. Okay, so first, let's start with the LLM adaptation life cycle. Maybe many of you already tried the LLM models, and you're familiar with the procedure. So the LLMs normally pass through several stages before they become useful in a real world application. The process begins with a large pre-trained foundation model, as you can see in the left side. Okay, and the model has typically learned general linguistic and factual patterns from large-scale datasets. But a general purpose model may not understand the terminology, workflows, policies, or preferences of a specific domain, right? So, therefore, it requires maybe additional adaptation, and domain adaptation already exposes the model to specialized knowledge, such as maybe medical, maybe legal, financial, industrial, or scientific information. And instruction tuning also improves the model's ability to following those task specific instruction. And after that, also we need something else. We need like alignment. So the alignment and preference learning also attempt to make its behavior more useful, safe, and consistent with human expectations to be usable. After deployment, the model may also require continual adaptation because user needs and also organizational knowledge and operating the environments change over time. So we have to update all the time. Um, so the main difficulty is that the data needed for these stages and is often distributed across multiple organizations and devices. So it's not only one. We have a number of devices. They are working and all the time it should be updated. So there are one of the difficulties in this case is this. So these participants may be unwilling or unable to transfer their own data to a centralized server, as I mentioned before, for training, for the global training. So this is exactly where federated learning can contribute in many practical scenarios. The objective is not to federate the extremely expensive pre-training of an LLM, large language model, from scratch. So it's not needed to start from scratch. We need to use some benefits, some methods to use the low amount of cost, low computational power, the less amount of communication. That's why instead, the more realistic objective is to federate its adaptation, instruction tuning, personalization, or continual learning. Okay, so after seeing this pipeline, why full fine tuning is difficult? This is one of the key questions. So fine tuning every parameter of the LLM is computationally expensive, as you know, because that's really huge. In especially considering the centralized learning, and in the centralized environment, that's expensive, and also in a federated environment the problem becomes more serious. Why? Because each participant already may need to store the model and perform local forward and backward propagation, right? So for doing that one and then communicating to the centralized server for maybe transferring the gradients, the parameters to the server. So we need the high amount of computational capacity as well as the communication, the bandwidth. So when a model contains billions of parameters, repeatedly transmitting full model updates can create an enormous communication burden. In addition, also maybe many of these clients maybe they can't have the sufficient amount of GPU memories. In many cases, they use maybe CPUs also. So they have the computational burden, especially. And that's the reason also most of practical Fed LLM, federated large language model, short for Fed LLM research, focus on parameter efficient adaptation rather than updating the entire model. And also, In case of parameter efficient fine tuning or short form PFT, it changes the adaptation strategy, right? So you can see in this figure the four famous like methods like prompt tuning, prefix tuning, adapters, and the LoRA, which is the most famous one among the others. You can see in these days, in the recent time, in many papers, they are using one or a combination of most of them together. So this is like parameter efficient fine tuning changes the adaptation strategy. Instead of updating all model parameters, we can freeze most or all the pre-trained model and optimize only a small set of additional parameters. Okay, that's gonna be helpful. Prompt tuning, as you know, is learns continuous prompt vectors, and prefix already tuning introduce like trainable vectors into multiple transformer layers. It's not only one from the starting point. In many layers, it can be usable. And adapter methods already insert small neural modules between existing layers. And LoRA, as you know, is represents the weight change using two low-rank matrices. And because only these matrices are trained, the number of trainable and communicated, maybe the parameters, can be much smaller than in full fine tuning, and is a good point. This makes PFT particularly attractive in federated learning, or short form FL, where both local resources and the network bandwidths are limited. And many people, that's why, are using LoRa these days. Also, since like 2 years ago, I'm using that one in most of my researches a lot. Okay, so let's see briefly the federated learning in one picture. So as you can see, maybe for those ones who don't know about federated learning, different types of clients, they are connected to one centralized server. This is the standard simple format of federated learning. So first of all, the server already have the global model and send it distributed among all of the clients as the initial model. So each client, like hospital, smartphone, enterprise, edge devices, you can consider different types. They already get the global model as the initial model, and after that each one has their own data set, so they update the model based on their own data set trained locally, and then prepare different types. For example, consider the gradient and or parameters, and then upload those parameters to the server. Server gathers all of the updates, and after aggregation, updating the new global model, and again redistribute among all of the clients. This process will be continue until they get the highest amount of like accuracy or any types of condition they already make in their optimization problem. So the main point is raw data remains at the client side and don't share. Okay, and also briefly about the simple mathematical like objective function optimization in case of federated learning. One of the famous method in federated learning is federated averaging, short form FedAVG. And as you can see, we have the aim is minimizing the weighted like combination of local objectives. And as you can see here, we try to minimize the f theta, and we have fk theta. Fk means the loss function of client k, and is multiplied with nk, which is the number of local training samples for that client k. So in federated averaging, the clients first perform several local optimization steps, and the server then calculates a weighted average of the locally trained models. And FadeAVG is also simple and effective. That's why in all, like I can say, until 3 4 years ago, most of the more than 95% of papers use FedAVG, and that's why they use it. But it wasn't specifically designed for models with billions of parameters. Low rank adapters, highly heterogeneous tasks, or conflicting client objectives. So that's why applying a standard FedAVG directly to LLM adaptation can be problematic these days. Okay, do you remember in slide 5, I already showed the life cycle for LLM? So that's one question. Is it good to apply federated learning in pre-training stage or post-training stage? Because as you know, if like federated learning can theoretically be introduced at several stages of the LLM life cycle. One possibility is federated pre-training, and also participants collaboratively like train a foundation model from distributed corpora. But you know, this is extremely demanding in terms of computation, synchronization, and communication also. So it's not good idea, right? So a more practical direction these days in federated learning is federated post training, and this includes domain adaptation, instruction tuning, alignment, personalization, and continual learning. These days, this is more common. And in these scenarios, participants begin with an existing pre-trained model and collaboratively adapt that one to private domains or tasks. And that's why Fed LLM shouldn't be understood as a single algorithm. It is a family of approaches covering different stages, exchanging like objects, aggregating mechanisms, and deployment, these types of settings. Okay, so it would be better to focus more on post training rather than the pre training in case of federated learning. And definitely, you know about the cross device versus cross silo in federated learning. These days, federated large language models also. As you know, in cross device, they have the peer to peer connection, number of clients they can connect. But in cross silo on the right side, we have the list number of big organizations like enterprise, hospitals, and they have most of the time the centralized connection together. And also, Fed LLM RD systems can generally be divided into these two different environments, and cross-device learning may involve thousands of millions of smartphones, personal computers, vehicles, or IoT devices. These clients have limited resources, the less amount, maybe CPUs also in many cases, and they including their own personal data, right? And but the opposite side is like cross zero, the right side, and this learning like involve a smaller number of organizations such as hospitals and universities, banks, others, and this participation is like usually more stable, and they may have stronger computing infrastructures, definitely many servers. But cross silo participants often have like kinds of stricter requirements concerning governance. This is one of the problem, or maybe IPs or accountability and model ownership. So the appropriate architecture therefore depends on who owns the data. This is very important the point, and who performs the computation and who is trusted to coordinate learning. So based on our scenario, we can consider we should go through cross device or cross silo. Okay, and then let's see about federated instruction tuning. So we can consider different types of clients from A like to D. They have connected to the centralized server, including global instruction tuned LLM. So instruction tuning teaches a pre-trained model to respond like appropriately to natural language instructions, and high quality instruction data is valuable, but it may be distributed across organizations and domains. A hospital may own like medical question answering data, right? And a company may have like internal support conversations, and educational institution like university may hold tutoring examples. So federated instruction tuning like allows these clients all together to improve a shared instruction following model, because each one they do their own job, but it had to work together. So without this model, without directly exchanging their raw data, so raw instruction response pairs, this can increase domain diversity and improve generalization. That's why these days some many others are focusing on this area. And at the same time, heterogeneous instructions may create optimization conflicts because clients may be teaching the model very different tasks and response styles. Definitely, because we have the diverse and heterogeneous clients. So let's see. As I mentioned, among the methods, the LoRa was very famous and is famous these days too. And federated LoRa, one communication round. Let's see. For example, we have a number of clients. On the middle, you can see from client 1 to K. All of them has connection to the server. And in this case, in Fed LoRa, the large pre-trained backbone remains frozen for make easier to train and be low cost. So the server distributes a shared LoRa adapter only, and each client updates that adapter using its local own data. And after local training, clients upload only the LoRa parameters rather than the entire model. The server aggregates these lightweight modules and sends the updated adapters back to the clients. And then this significantly reduces the number of trainable and transmitted parameters, definitely. It can also make it easier to maintain separate adapters for different domains or users. But you know, the approach, these types of approach still requires clients to run forward and backward propagation and through this like base model. And local memory and computation remains important constraint. That's a big problem. So in this slide, you can see make comparison with different already aspects. For exchange object, what is the pros, what is the cons, strengths, limitation. And federalism is not like limited to exchange model weights. Different system may communicate different learning objects. Like full model updates are expressive but extremely costly. And adapter or LoRa parameters are much smaller, but their structure creates new aggregation challenges, as you saw. And prompt and prefix parameters are even lighter because that one consider, for example, prompt from starting and the prefix in some layers. So although they may not like provide enough adaptation capacity for every task, although that's light. And another possibility is knowledge transfer through logics or like intermediate representations. And this can also allow clients to use different model architecture, but it may require like public or like maybe kind of references data set for distillation. That's a kind of difficulty. And consequently, deciding what to exchange is one of the most fundamental Fed LLM design choices that the author should pick. Okay, and also why, in case of, do you know the naive LoRa, which is very famous, but the naive LoRa aggregation doesn't work well and can be failed. Um, because like LoRa update is most of the time like represented as the product of two low-rank matrices like A, BK, and AK. So a simple implementation might average all client A matrices and all client B matrices separately. Okay, so but considering this one, like multiplying the two average factors introduces cross-client terms. So in general formats, like this is not equivalent to averaging the actual weight update BKAK together. So the difference can create aggregation noise and reduce model quality. The issue also becomes more difficult when clients use different LoRA ranks because of heterogeneous computational resources. Also, the methods like FLoRA is famous, already propose alternative kinds of aggregation strategies, including maybe stacking client factors rather than naively averaging that. And that's a better way. These days, many others are using that one. And also, let's see, I'm going to talk about global knowledge versus local personalization because in federated learning, like pure one, these days, like, so from since 2 years ago, personalization is more, people more willing about that, and that works better. Like considering the personal model for each client and the global model as a shared model on the middle. So each client have like updating when they're updating their model, updates the global format and also update the personal one, but personal will keep inside for inside of the like client area for keeping the privacy to avoid eavesdropping or use the third party use that one. And we these days consider two different accuracy for global as well as of course personalized one. So the federated learning traditionally already aims to construct a single global model, but client distribution may differ too significantly for one model to serve everyone equally well. So a useful strategy is to separate global and local already knowledge. The global adapter captures patterns that are beneficial across client. The local adapter already retains clients specific information such as maybe terminology, preferences, language, or institutional like policies. During inference, these like components may be like combined using a fixed or input depend weight. And after that, this approach allows clients to benefit from collaborative learning without losing like their local like kinds of specialized and also keep that one personalized and but this personalization is not like an optional feature in many like federated large language model system. It is core design objective. So these days, if you consider on large language model, it would be better also to focus on personalized side and keep the large language model, the base model frozen, and just working with adapters in this scenario to get the better results in a short time with low amount of computational power and others. And also, we have the hierarchical federated LLMs these days. It's come from hierarchical federated learning. So instead of just connecting the clients to the cloud server, on the middle, we have an extra layer, which is the edge side, regional edge aggregators. So in hierarchical Fed LLM architecture, clients don't necessarily communicate directly with one central cloud server. Devices or organizations can first send their updates to regional edge aggregators. For example, in smart homes, we have as example clients like smart watches, phones, everything, home appliances send their like updated models to the edge server inside the smart home, and then that one sent to the cloud side, which is including the large language model. So that one is a good one because the edge layer can aggregate the updated model. And if some, because in case of trust, if some issue happen, the malicious client, anything, uh, we can protect the cloud from those types of issues, and the edge home or the edge side can just face issue, and we can separate that edge home from others. This is for example, I'm also working on this area these days in the smart home. So in case of trustworthy, that's a very common scenario. And these edge servers combine local knowledge before communicating with the cloud. And such as this types of architecture can reduce long distance communication, lower latency, and support regional personalization. And for example, clients in one geographic region may share language, network, or application characteristics that differ from another region, but hierarchy also introduces additional questions. First, what should be aggregated at each level? And the next question, how frequently should cloud synchronization occur? And the next question, and how should trust be managed across multiple aggregators? So there are room to discuss in this scenario and this area. Okay, and let's see the federated learning large language model challenges in one map. So as you can see, we have like statistical heterogeneity challenge, task heterogeneity, system heterogeneity, evaluation and governance, and also communication, as well as communication, which is the most important, and many people are trying to uh, tackle these types of issue, and privacy, and also security and safety. So we have these types of challenges that I'm gonna talk about those ones in more details. For example, one of the challenges, as you saw, it is statistical and task heterogeneity. So traditional like federated learning already faces non-ID data already. So for LLMs also, heterogeneity can be much richer. One client may contain medical question answer pairs. Another may focus on like financial summarization, or the other one may perform like translation or code generation, different types of tasks, right? So clients may also differ in language, writing style, or maybe response length, and safety policy and data quality. So consequently, their local gradients may point in different directions. Naively, like averaging these updates also can cause negative transfer, slow convergence, or reduce performance for like minority clients. So federal aggregation must therefore consider not only like sample count, but also trying to task similarity, update compatibility, client quality, and personalization requirements. These are the challenges related to this area. The next challenge related to the FedLLM is system and model heterogeneity. So FedLLM participants may have highly heterogeneous resources. An enterprise server may train a high rank LoRA adapter, while an edge device may support only a small adapter or a subset of model layers, different really, and requiring every client to use the same architecture may exclude resource constraints kind of participants. On the other hand, also we have this allowing this uh, arbitrary local maybe architectures makes aggregation more difficult, right? So the heterogeneous ranks, layer selection, like kinds of quantization levels and model sizes must therefore be handled explicitly. This is very important point. And a practical system may adapt each client's workload according to its memory, computation, bandwidth, and energy availability while still preserving a meaningful shared representation. Those challenges and issues are in this area. And the next challenge, as I mentioned, that's very famous, which is communication as well as computation, cost challenging in the federated learning and these days Fed LLM. So the communication efficiency is one of the like original motivations for federated learning, but it becomes also specifically important for LLMs too. The uplink cost can be reduced by communicating adapters, compressed updates, or only selected modules. However, what about downlink? Downlink cost may remain substantial if the base model must be frequently transferred. That's why these days in some papers, the others, also in my previous paper, we didn't, we just use the base freeze model when it's really the quality and the accuracy of the global model wasn't good. That's why at that time the edge layer asked the cloud layer for using that model. Otherwise, we didn't use that one to reduce the communication. And in case of the downlink, so this is like kinds of issue. So many others trying to find a way to avoid that one and reduce the downlink cost too. And local training also requires activation memory and repeated forward and backward propagation through a large model. Even if most weights are frozen, therefore a communication efficient method is not automatically computation efficient or energy efficient. That's right. We have different scenario. So a complete system design must jointly optimize all of these resources rather than reporting only the number of trainable parameters. That's why these days also many others are working on this area. And the other challenge is about the privacy. Privacy is not automatic, right? This is very important one. So federated learning reduces the need to transmit raw data, but model updates can still reveal information about kinds of like local training examples. In Fed LLMs, sensitive information may appear in adapter updates, gradients, prompts, instruction data, or generated outputs. So secure aggregation can prevent the server from observing individual clients' updates by revealing only their aggregation. And also differential privacy, one of the famous one in this area, can limit the contribution of individual records or clients by clipping updates and adding kinds of like calibrated noise, and that's very important in case of DP, differential privacy. These mechanisms provide different like protections and costs. Secure aggregation hides individual updates from the aggregator, while differential privacy provides a statistical privacy kinds of and kinds of guarantee, but may reduce model utility. This is one other challenge. And privacy must therefore be defined through an explicit threat model. And in case of the next challenge, this is a security, poisoning, and safety. So a malicious client, these days, this is one of the famous maybe area, and there are many rooms to discuss. So malicious client can manipulate its local data or directly modify its updates in order to influence the global model. And traditional attacks may reduce accuracy or insert a backdoor activated by a specific like trigger that was common. But in federated instruction tuning, an attacker can also target alignment. The resulting global model may remain effective on ordinary benchmarks while becoming more willing to generate harmful or policy violating responses. This is particularly difficult because adapter updates are high dimensional and maybe this is the legitimate like client updates are already heterogeneous. So defenses must therefore access not only the maybe magnituding of an update, but also its behavioral like consequences, maybe semantic effects and consistency with safety requirements. So after seeing that one, the next part is trust and runtime assurance. So as you can see, the most federated system evaluate robustness after training, right? However, these real kinds of deployment require continuous assurance during operation. This is why considering during the process is important. So the system should monitor client behavior, update drift, model behavior, and downstream impact. When abnormal behavior is detected, it should determine whether the issue is caused by malicious activity, poor quality data, distribution shift, or system failure. So, in case of like, if you focus more on not just AI, more security side, we have many room to discuss in runtime enforcement. So the runtime enforcement may include reducing a client's aggregation weight, rejecting an adapter, and maybe quanting participation, rolling back to a trusted checkpoint, or activating a safe fallback model. And importantly, detection without a containment and recovery mechanism is incomplete isn't complete, so is incomplete one. So trustworthy fed LLM systems need both monitoring and also actionable enforcement at the same time. Okay, so after seeing those challenges, also let's see a multidimensional evaluation framework. And this is like a Fed LLM system shouldn't be like judged only by averaging accuracy or language model loss. This is unfortunately many in many papers this is common, only focusing on that area too. We need to evaluate generalization to unseen tasks, personalization for individual clients, and performance for the worst served clients. System metrics should include communication volume, peak memory, latency, computation, and energy. Privacy and security evaluation should measure attack success, information leakage, detection rate, false positive rate, and resilience after recovery. We should also examine participation failure and whether maybe resource constrained or minority clients benefit from the global model. So a method that improves average utility while excluding weaker clients may not represent a successful federated system. And when FedLLM create value, so where it's creating value, you can see FedLLMs are especially valuable when several participants possess complementary knowledge but cannot pool their raw data. Hospitals may collaboratively adapt a clinical assistant while protecting patient maybe records And banks may improve fraud analysis or financial language models without revealing customer transactions. And enterprises may build shared domain in maybe intelligence while returning internal documents, and educational institutions can collaborate across different courses, languages, and student populations. So edge devices also can personalize maybe compact assistance using local interactions and context. The strangest use cases are the four, not simply those with large datasets. They are situations in which collaboration adds value, while centralization is technically, legally, or commercially maybe undesirable. So we can focusing on these values for Fed LLM. And also, here there's representative use cases. Considering a like kinds of group of hospitals that wish to improve a medical question answering model. So each hospital has different specialties, or the patient population requires something. So federated adaptation can combine this distributed maybe expertise without building one central patient database. In enterprise AI, organizations may share general domain patterns while retaining confidential policies, reports, and IP locally. Okay, so multilingual Fed LLMs can also learn from geographically distributed language communities, particularly where public training data is limited. And finally, personal devices can adapt assistance to user preferences, writing like kinds of styles, and recurring tasks. In each case, the objective is to share useful learning while preserving local control. Keep everything local. And in this slide, I'm gonna talk briefly about what I am doing these days, or what I did in some years since some years ago. So the selected directions on our research area, we have been like investigated how to move beyond uniform exchange of like complete model updates from the left side, as you can see. Like one direction is selective module exchange, where the system communicates only the LLM components that provide sufficient benefits related, maybe relative to their communication and energy costs both. And a second direction on the middle is hierarchical personalization, which separates global, regional, and client kinds of specific knowledge. And the right side, a third direction, is behavior driven trust and runtime assurance, rather than assuming that every participant remains trustworthy. The system monitors client and model behavior and applies maybe containment actions when necessary. These directions already share one principle: federated intelligence should be adaptive to the model, the client, the network, and the operational risk. And okay, after seeing that one, right now let's see federated retrieval augmented generation, in short form, Fed RAG, that's common these days. So fine tuning is not the only way to use distributed knowledge. Retrieval augmented generation allows an LLM to retrieve external evidence and at inference time. Okay, so in federated RAG, the kinds of relevant knowledge repositories remain distributed, And the system may route a query to select resources, retrieve protected evidence locally, or exchange compressed and privacy filtered knowledge. And this can reduce the need to embed every piece of maybe changing knowledge into model parameters. But the retrieval itself creates kind of privacy challenges. Like among the challenges, we have the query content, source selection, document relevance, and returned kinds of evidence may all disclose like sensitive information that we should think about that. And the future federated RAG systems maybe must jointly optimize retrieval quality, access control, communication, as well as privacy. Okay, so um, before finishing, let's also see federated, multimodal, and agentic AI, which is famous these days. The and also in future definitely it will works better and better. Future federated foundation models will increasingly be multimodal. Definitely clients may hold different combinations of text, images, audios, videos, and maybe sensor data. This creates modality and also heterogeneity in addition to maybe task or resource heterogeneity. So some of clients may train vision language conductors, while the others like adapt language or sensor like processing modules. Another also emerging direction is federated agents. And as you can see on the right side, each agent may have local memory, private tools, environmental observations, and organization specific objectives. And the agent could maybe collaborate by sharing policies, adapters, maybe summaries or experiences without exposing their complete local state. This moves the problem from federated model training toward federated decision making and coordination. Okay, and let's check and see kinds of sustainable and continual Fed LLMs. So the real world LLM deployments these days are not static, definitely. New documents, tasks, users, languages, and risk already appear continuously. And federated kinds of continual learning must incorporate new knowledge without maybe forgetting kind of previously learned capabilities, right? So it must also operate when clients join, leave, or change their data distributions. And sustainability is equally important. The system may adapt LoRA ranks, select only maybe energy efficient clients, reduce unnecessary communication runs, or transmit only the most useful modules. And the goal shouldn't be like only maximum accuracy, maximizing the accuracy at any resource cost. It should be a stable and useful learning process that respects energy, maybe latency, participation, and environmental constraints over long periods. And okay, let's see. Right now we have some open research questions. As you can see, 7 important ones are here. So the field still lack definitive answers to several fundamental questions. We need to determine the appropriate units of collaboration, like parameters, adapters, prompts, kinds of representations, maybe knowledge or agent experiences. So aggregation must handle different ranks, architectures, tasks, and maybe reliability levels. And in case of personalization, must preserve local expertise without maybe fragmenting the shared model. Security mechanisms must move from detection towards maybe containment and kinds of recovery. And evaluation must reflect privacy, definitely, and safety, fairness, communication, and also energy and worst client performance. And finally, federated governance will become increasingly important as clients evolve from passive data owners into autonomous agents capable of making decisions and using tools. And I would like to leave you with three main takeaways. First, federated learning provides an important framework for learning from distributed private data, but it shouldn't be described as an automatic privacy guarantee. And second, parameter efficient techniques such as LoRA make federated LLM adaptation sustainably more practical. However, small updates don't eliminate the challenges of aggregation, computation, heterogeneity, leakage, poisoning, and safety. And the third one, the future of this field extends beyond federated fine tuning. It includes federated retrieval, maybe multimodal models, and personalized adapters, and autonomous agents, continual learning, and runtime maybe assurance. So the ultimate objective is not merely a decentralized model, but trustworthy collaborative intelligence. So these are all related to the federated large language model that I prepared for today. And thank you very much for your attention. I would be happy to hear your questions, comments, and perspectives. Thank you very much.
Thank you, Dr. for your inspiring, insightful question.
Hello, Dr. Faranak.
Yes, hello.
Yeah, I was just listening your lecture. It was very insightful session. Thank you very much.
I appreciate you.
Uh,
Thank you.
I have a question. Can you tell me what is the biggest limitation of federated learning when applying to the real world problems?
Uh,
Major limitation of federated learning.
hmm, yes. In case of like limitation federated learning, there are not only the federated, just the pure federated learning. Are you talking without LLM?
Not right now, but I'm planning to work on federated learning.
Okay. So, in case of federated learning, for example, these days, one of the important challenges is when you use, especially at the LLM side, we have heterogeneous clients. So, the different clients using different data sets, different types of data, and different tasks they are doing. So, making a model, especially consider we have a number of clients, different formats, heterogeneous one, and also these ones wanna focus on make their personal data. This is the highest challenge in the federated and large language model. So we have to find the high accuracy personalized model and evaluating all the time in each step. So that's a right now, to be honest, blue ocean, not red ocean for doing research. If you can find a way to keep the privacy and also improve the accuracy of personalized model as well as the global model. And also the other kinds of challenge and room to discuss, the common one is focusing more on trustworthy these days. If you will be like familiar with the security side and using not just maybe encryption, not the simple encryption. If you focus more enforcement learning during the training process also can be helpful. So I can say in case of like challenges and difficulties is these ones.
Okay, okay. Means you mean heterogeneity is the like biggest hurdle while implementing the federated learning models.
Heterogeneity just in simple federated learning is these days we can already solve the problem and improve the accuracy and optimizing the problem. But if we add also the large language model and want to get the personalized model and the global model, yeah, that's the difficult one right now these days.
Okay, thank you. That's from my side. Thank you.
Thank you.
Which knowledge should be global or which knowledge should be personalized? In Federated development, how do you decide that which knowledge should be global and which knowledge should be personalized? Because if you keep some data locally and keep some data globally, then how do you decide?
I'm not sure I heard your question well or not, but one time I say your question. You already mentioned about the global model, keep the personalization in global model, and how to keep the accuracy that one high, right? Am I correct?
Right.
Okay.
So,
Yes. Okay. Thank you. So in case of like personalization, I wanna show it one more time. Okay, so okay. Consider like we have maybe 100 clients, okay, and each like 10 clients are living in one smart home. Okay, I want to explain as an example. So for example, you and family members, you are using different types of maybe Mi Band, maybe smartphone, maybe different appliances. Those are connected to your maybe router, the Wi-Fi. So all of these devices are using the Wi-Fi, and maybe one of the family members don't want to share the personal data with the server and with the other family members. Maybe I don't know, maybe some about, I hope not happen, but about the disease or some illness is just tracking the heart beat or something by using the wearable device. And you wanna keep the information and is tracking the information all the time continuously. So what's gonna happen if someone can eavesdropping get the information, so it's gonna be problem. That's why we have the personalized, and each client, each device has their own personal data and personalized model. So we can consider, in case of federated learning, we have the in the past we have split federated learning, just cut the model to the client side and server side. But these days the development is, we have the shared model, which is the same parts or similar parts for each devices as a shared model, as a global model, and we have the personalized model. Okay, so for example, device 1, device 2, device 3, device 4, they have the light, maybe MLP, and consider as the personalized model, and apply differential privacy for protection. And after that, just update when each device updates the model to in their own data set. Don't share that personalized one with the server. But how it gonna works? Instead, just share the shared model, which is common and public among all of the models. Share that one to the server with one also part. It's including the weight without any information for maybe uh, leaking the information about each client. It is related to the personalized side. So in that package, including the information of each device, and all of them will be gathered in the smart home as an edge layer. And after that, when the edge layer aggregates a model, so it's aggregating the model, which is the shared model, right? Gathering that one and aggregating and updating the global model, and check if the information and the accuracy of the shared model is maybe higher than the condition. Okay, it's not needed to connect to the cloud server to use the LLM. So in that case, just the edge will redistribute the updated shared model with others. And we had one package. It's kinds of related to the personalized models of each device. So that one in the edge will understand which information is comes from which device. So because the edge already knows which types of already devices is connected. So updating that one and share that package also with the shared model to the specific clients, and the clients will use the updated of that one with the shared model and using their own local dataset update the model. So that's why the model, also personalized model accuracy will be improved, because the edge data set already gets that one, the weight related to each client for personalized model, and updating that one, but shared only with those clients, not with others. We have the shared and we have the personalized one.
One more question. One more question. Actually, I have done PhD in machine learning. I want to ask you if I want to pursue postdoctoral research in federated LLM, which research direction would you suggest? If I want to pursue postdoctoral in federated LLM, which direction would you suggest?
I'm
Which
sorry,
research?
but you related the personalized the Fed LLM. What is? Could you? Is it possible to write your comment here? Is it possible to write in chat bot in chat part? Thank you.
Okay, guys, is my voice audible to you? Is my voice audible to you? Hello? Alright. Is my voice audible to you? Which different direction will you suggest? And what's your
Is it visible? Okay. I recently completed my PhD now. I'm looking for postdoc, which, okay, research direction is best in federated learning. Uh, may I ask what was your previous research area?
machine learning?
Machine learning. Machine learning. Okay, okay, got it. So that's a tough question to answer because if you wanna just focus on federated learning, the pure federated learning is blue ocean. It's not blue ocean, it's red ocean, definitely. And writing high quality papers is not easy right now. I think it would be better focus on large language models in one side, federated learning, and these days the trend is trustworthy. Okay, try to find the malicious and the attackers not from outside of the system, inside of the system. Sometimes some clients um, inside the system are malicious and they will already malicious the server and others. So try to find those ones and stop that using the protocols, considering the privacy of the network. This is the already the blue ocean, and there are many rules to discuss. You can focus on that one, not the pure federated learning. And federated learning just used as the key point for keeping the privacy during the training process.
Thank you, Dr. Solat, for such an insightful and engaging keynote address. On behalf of organizing committee of ICAAIDT 2026, I extend our heartfelt gratitude to Dr. Frank Solar, Assistant Professor in Schools of Artificial Intelligence and Data Science at Sejong University, South Korea, and a PhD graduate from our Department of Computing at Gachon University for delivering such an insightful and thought-provoking keynote address. Thank you for taking the time to share your knowledge and expertise with us. It has been our privilege and honor to have you with us today. Thank you once again, ma'am. It was a great pleasure having you with us.
Thank you very much. Have a nice day. Bye bye. I appreciate you. Thank you.